Hello, my name is Jaydeep Sai, and the topic given to me in this tech talk is distribution functions and expectations. Expected value. In probability theory, the expected value, also called expectation, expectancy, mathematical expectation, mean, average, or first movement, is a generalization of weighted average. Informally, the expected value is the arithmetic mean of a large number of independently selected outcomes of a random variable. So, expected value. In the probability theory, the expected value is also called as expectations, expectancy, and also mathematical expectation. It's also called as mean, average, or the first movement. Is a generalization of the weight average. Informally, the expected value is the arithmetic mean of a large number of independently selected outcomes of a random variable. So the expected value is also called as the arithmetic mean of the large number of the independently selected outcomes. The expected value of a random variable with a finite number of outcomes is the weighted average of all possible outcomes. In the case of a continuum of possible outcomes, the expectation is defined by integration. So the expectation is defined by the integration in the axiomatic foundation for probability provided by measure theory. The expectation is given by Lebesgue integration. So in the axiomatic foundation, the probability provided by the measure theory, the expectation is given by Lebesgue integration. History of the expected values. The idea of the expected value originated in the middle of the 17th century for the study of the so-called problem of points. So the expected values are originated in the middle of the 17th century for the study of the problems of point, which seeks to divide the stakes in a fair way between two players who have to end their game before it is properly finished. The problem has been debated for centuries. So there was a problem for the fair way between the two players. So to have to end their game before it is properly finished. So to finish the game properly, the expected values are implemented. This problem has been debated for centuries. Many conflicting proposals and solutions have been suggested over the years. When it was proposed to Blaise Pascal by French writer and amateur mathematician Chevalier de Mere in 1654. Mere claimed that this problem couldn't be solved and that it showed just how flawed mathematics were when it came to its application to the real world. Pascal, being a mathematician, was provoked and determined to solve the problems once and for all. So it is the history of the expected values. The idea of the expected value originated in the middle of the 17th century. So this expected value study is originated in 17th century to calculate the fairness of the two players. So it was very difficult to make the fair results of the game. So there was many debates that the player would win or not. So there were many theories given by the historical scientists, and the Blaise Pascal by French writer and amateur mathematical calculator in 1654 claimed that this problem couldn't be solved, and that is showed just how clear mathematics was when it came to its application to the real world. He began to discuss the problems in the famous series of letters to Pierre de Fermat. Soon enough, they both independently came up with a solution. They solved the problem in different computational ways, but their results were identical because their computations were based on the same fundamental principles. The principle is that the value of a future gain should be directly proportional to the change of getting it. The principle seemed to have come and naturally to both of them. They were very pleased by the fact that they have found both are essential the same solution, and this in turn made them absolutely convinced that they had solved the problem consecutively. However, they did not publish their findings. They only informed a small circle of mutual scientist friends in Paris about it. So they were two scientists and who were independently came with a solution. They solved the problem in different computational ways, but their results were identical because their computations were based on the same fundamental principle. The principle is that the value of a future gain should be directly proportional to the change of getting it. This principle seemed to have come naturally to both of them. They were very pleased by the fact that they have found essentially the same solution, and this in turn made them absolutely convinced that they have solved the problem consecutively. So, however, they did not publish their findings. They only informed a small circle of mutual scientist friends in Paris about it. In Dutch mathematician Christian Huygens' book, he considered the problem of points and presented a solution based on the same principle as the solutions of the Pascal and Fermat. Huygens published his paper in 1654. See Huygens 1657. The ratio Sinis in Ludo on the probability theory just after visiting the Paris. The book extended the concept of expectation by adding rules for how to calculate expectations in more complicated situations than the original problem. Example, for three or more players, and can be seen as the first successful attempt to laying down the foundations of the theory of probability. So the Dutch mathematician Christian Huygens' book, he considered the problem of the point and presented a solution based on the same principle as the solutions of Pascal and Fermat. Huygens published his treatise in 1657. So on the probability theory just after visiting the Paris. The book extended the concept of expectations by adding rules for how to calculate the expectation in more complicated situations than the original problem. Example, for three or more players, and can be seen as the first successful attempt at laying down the foundations of the theory of probability. Etymology. Neither Pascal nor Huygens used the term expectation in its modern sense. In particular, Huygens writes that any one chance or expectation to win anything is worth just such as some, as would occur in the same chance and expectation at a fair lay. If I expect A or B and have an equal chance of gaining them, my expectation is worth A plus B by 2. More than 100 years later, in 1814, Simon Laplace published his tract where the concept of expected value was defined explicitly. So the concept of etymology was developed, and the Pascal and the Huygens were used the term neither used the term expectation in its modern sense. In particular, Huygens writes that any one chance or expectation to win anything is worth just such as some, as would occur in the same chance and expectation it fairly. If I expect A or B and have an equal chance of gaining them, my expectation is worth A plus B by 2. More than 100 years later, in 1814, Simon Laplace published his tract where the concept of expected value was defined very explicitly. This advantage in the theory of chance is the product of the sum hoped for by the probability of obtaining it. It is the partial sum which to result when we do not wish to run the risks of the event in supposing that the division is made proportional to the probabilities. This division is the only equitable one when all strange circumstances are eliminated, because an equal degree of probability gives an equal right for the sum hoped for. We will call this advantage mathematical hope. Notations. The use of the letter E to denote expected values goes back to W. Whitworth in 1901. So the notations were given to the expected values, and the letter which is denoted by E denotes the expected values, which was given by the W. Whitstone in 1901. The symbol has become popular since then for English writers. So this letter E was becoming very popular in the English writers. In German, E stands for Erwartungswert. In Spanish for Esperanza Mathematica, and in French for Mathematique. When is used to denote expected value, authors use a variety of stylization. The expected operator can be stylized as E upright, E italic, or E in background bold, while a variety of bracket notations such as E of x, E of step x, and EX are also used. Definition. As described below, there are several context-dependent ways of defining the expected value. The simplest and original definition deals with the case of the finitely many possible outcomes, such as in the flip of a coin. When the theory of infinite series, this can be extended to the case of countably many possible outcomes. It is also very common to consider the distinct case of random variable dictated by piecewise continuous probability density functions, as these arise in many natural contexts. All of these specified definitions may be viewed as special cases of the general definition based on the mathematical tools of measure theory and Lebesgue integration, which provide these different contexts with an axiomatic foundation and common language. So the definition of the expected value as described below, these are the several context-dependent ways of defining the expected value. The simplest and original definition of deals with the case of finitely many possible outcomes, such as in the flip of a coin. With the theory of infinite series, this can be extended to the case of countably many possible outcomes. It is also very common to consider the distinct case of random variables dictated by piecewise continuous probability density functions, as these arise in many natural contexts. All of these specific definitions may be viewed as possible case of the general definition based upon the mathematical tools of measure theory and Lebesgue integration, which provide these different contexts with an axiomatic foundation and common language. Random variables with finitely many outcomes. Let X represent the outcome of a roll of a fair six-sided die. More specifically, X will be the number of pips showing on the top face of the die after the toss. The possible values of X are 1, 2, 3, 4, 5, and 6, all of which are equally likely with a probability of 1 by 6. The expectation of X is E of X is equals to 1 into 1 by 6 plus 2 into 1 by 6 plus 3 into 1 by 6 plus 4 into 1 by 6 plus 5 into 1 by 6 plus 6 into 1 by 6. So the total is 3.5. The formula is x into f of x. If one roll the die n times and computes the average arithmetic mean of the results, then as n grows, the average will almost solely converge to the expected value, a fact known as the strong law of large numbers. So if one roll the die n times and the computes the average arithmetic mean of the results, then as n grows, the average will almost surely converge to the expected value, a fact known as the strong law of large numbers. Random variables with countably many outcomes. Informally, the expectation of a random variable with a countable set of possible outcomes is defined analogously as the weighted average of all possible outcomes, where the weights are given by the probabilities of realizing each given value. This is to say that E of x is equal to summation of the I to infinity xi pxi pi. So random variables with density. Now consider a random variable x which has a probability density function given by function f on the real number line. This means that the probability of x taking on a value in any given open interval is given by the integral of f over the interval. The expectation of x is then given by the integral e of x is equal to integration of from minus infinity to infinity x into f of x dx. Arbitrary real valued random variables. All definitions of expected value may be expressed in the language of measure theory. In general, if x is a real valued random variable defined on the probability space, then the expected value of x denotes by e of x is defined as the Lebesgue integral. E of x is equal to integration from whom to x dot d of p. So it is the arbitrary real value random variables. And now infinite expected values. Expected values I've defined above are automatically finite numbers. However, in many cases, it is fundamental to be able to consider expected values of plus or minus infinite. This is intuitive. For example, in the case of the St. Petersburg paradox, in which one considers a random variable with possible outcomes xi is equals to 2 into I, which associated probabilities pi is equals to 2 minus I for I ranging over all positive integers according to the summation formula. In the case of random variables with countably many outcomes, one has E of x is equals to summation of I is equals to 1 to infinity xi into pi is equals to 2 into 1 by 2 plus 4 into 1 by 4 plus 8 into 1 by 8 plus 16 into 1 by 16 plus so on is equal to 1 plus 1 plus 1 plus 1 plus so on. So it is the infinite expected values and given by the formula E of x is equals to summation of the I to 1 I from 1 to infinity xi p of xi. Inequalities. Concentration inequalities control the likelihood of random variable taking on large values. Markov's inequality is among the best known and simplest to prove. For a non-negative random variable x and any positive number a, it states that p of x greater than or equal to a is less than or equal to e of x by a. If x is any random variable with finite expectation, then Markov's inequality may be applied to the random variable step of x minus e of x by 2 to obtain inequality. And it is the formula for the inequalities. And now going to relationship between characteristics functions. The probability density function f of x of a scalar random variable x is related to its characteristic function psi of x by the inversion formula. F of x is equals to 1 by 2 pi integration from r e power minus itx psi of x into t dt for the expected value of g of x where g belongs to r is a Borel function. We can say this inversion formula to obtain e of g of x is equals to 1 by 2 pi integration of g of x and in the interval or e power minus t of x I x of t dt into dx. Uses and applications of the expected values. The expectation of a random variable plays an important role in the variety of the context. For example, in decision theory, an agent making an optimal choice in the content of incomplete information is often assumed to maximize the expected value of their utility function. For a different example, in statistics, where one seeks estimates for unknown parameters based on the available data, the estimate itself is a random variable. In such settings, a desirable criterion for a good estimator is that it is unbiased. That is, the expected value of the estimate is equal to the true value of the underlying parameter. So these are the uses and the applications. The density, the expectation of the random variable plays an important role in a variety of the contexts. For example, in decision theory, an agent making an optimal choice in the context of incomplete information is often assumed to maximize the expected value of their utility function. For a different example, in statistics, where one seeks estimates for unknown parameters based on the available data, the estimate itself is a good random variable. In such setting, a desirable criterion for a good estimator is that it is unbiased, that is, expected value of the estimate is equal to the true value of the underlying parameter. So T is possible to construct an expected value equal to the probability of an event by taking the expectation of an indicator function that is 1 if the event has occurred and 0 otherwise. The relationship can be used to translate properties of the expected value into properties of probabilities. Example, using the law of the large numbers to justify estimating probabilities by frequencies. So T is the probable possible to construct an expected value equal to the probability of an event by taking the expectation of an indicator function that is 1 if the event has occurred and 0 otherwise. This relation can be used to translate properties of the expected values into properties of probabilities. Example, using the law of large numbers to justify estimating probabilities by the frequencies. I thank the faculty and the institution for giving me the opportunity to speak on the given topic. Thank you.